Hello, and welcome back to Adams Academy. My name is Lauren, and I am here with the rest of Group 7, Jesse, Marcelo, Victoria, and Jethro. We were given the following scenario to analyze. A normotensive rat was surgically prepared for intravenous infusion and arterial blood pressure measurement so that drugs could be infused chronically and arterial pressure could be measured continuously. The animal fully recovered from the surgery and was fully conscious and healthy 1 week before the experiment started. During the 3-day experiment, the conscious rat was continuously intravenously infused with a peripherally acting alpha-1 adrenergic receptor agonist. The amount of drug administered was varied using a computer-controlled pump to generate the indicated effect. During the first phase of the drug infusion, mean arterial pressure rose linearly from 100 to 120 millimeters of mercury during 3 hours. During the second phase of the infusion, the MAP rose more slowly over the next 45 hours, reaching 150 millimeters of mercury by 48 hours. During the third phase of the infusion, sorry about that, guys. Let me make that a little more clear. During the third phase of the infusion, from 48 to 72 hours, the level of MAP declined moderately as the MAP was found to be 140 millimeters of mercury at 72 hours. Following assumptions were made when we began our analysis. Firstly, we assumed that during the mouse's recovery week, it became comfortable with its environment, such that there was no reason for elevated blood pressure or heart rate prior to the alpha-1 adrenergic agonist injection. If the rat had elevated sympathetic nervous system activity prior to the experiment, we would have had a background increase in blood pressure, which would have made isolating the effects of the drug rather difficult. We are also assuming that the drug being used is completely selective for alpha-1 receptors, and that the drug's other effects on the coronary arteries supplying the heart rate are overcome by the heart's autoregulatory capabilities. If the drug was chronotropic, for example, it would potentially induce electrical conduction effects of the heart, which would affect the blood pressure measurements. Lastly, we are assuming that the rat we are using is representative of all rats as well as rabbits. We will be proposing a possible explanation of the scenario based on a paper that used rabbits as their experimental animals.
So during phase 1, we have an increase from 100 to 120. As the blood vessels begin to constrict, we have a decrease in radius, an increase in resistance, and a decrease in blood flow. There's more contact with the blood vessel wall which is occurring, which is what causes that increase in blood pressure. As the blood begins to contact the blood vessel wall, we trigger the stretch receptors to send signals to the medulla, which then increases the parasympathetic and decreases the sympathetic nervous system. This results in decreased heart rate, decreased force of contraction, and a decreased cardiac output. There will be an attempt to increase dilation, but since the constriction is occurring from a drug, this will fail and constriction will continue. The baroreceptors respond within seconds, but as we go near the end of the 3 hours, this is where the baroreceptors begin to reset and renal controls start to come in. Because the phase 3 is still considered acute, there are no permanent changes that occur. But we do have a change in that blood pressure and heart rate sigmoid curve, which normally looks like this, is going to be shifted over towards higher blood pressure, and we are going to see a decrease in that heart rate.
All right, so moving on to the second phase of the infusion, we are told that the mean arterial pressure rises much more slowly, as you guys can see in the graph, compared to the first phase. And it rises over the next 45 hours, so from about 3 hours to 48 hours, over there. And it rises from 120 millimeters of mercury to 150 millimeters of mercury. The question that we seek to answer here is, what is occurring to the systems in the body during this slow rise in blood pressure? So the slow rise in blood pressure may have to do with the variability in alpha-1 agonist infusion. If the mouse in phase 2 was infused with a lower dose of the drug when compared to phase 1, then that means that it would not have as intense of a response to the drug as it did during phase 1. So the variability in drug could have affected the vasoconstriction within the vessels, as less drug may have been acting on them. Other factors that may have also been affected during the slower rise in blood pressure could also include the resetting of the baroreceptor and increased renal control, which was mentioned before also in phase 1. The kidneys may begin to secrete less salt in an attempt to excrete more water in order to decrease the blood pressure. So, thinking about it as well, if the concentration of the drug stayed constant or changed very little, another system that may have had a part to play takes into account desensitization of the rat to desensitization, that's spelled completely wrong, desensitization. There we go. And the desensitization would be specific to the alpha-1 agonist that is being infused. Since the rat is undergoing constant infusion and has been for an extended period of time, its cells may be desensitizing themselves to the drug. When looking into additional research on this topic, I ended up finding a paper by Gerdal, Khan, and Uger that was written in 2005. This paper looked at prolonged exposure, in their case 6 to 12 hours, to the drug phenylephrine, which is also an alpha-1 agonist. Their experiment found that the prolonged phenylephrine infusion actually led to an increase in nitric oxide synthase activity, allowing for more nitric oxide, so increased NO, to be produced. Nitric oxide is a vasodilator, and its increased production in their experiment led to increased vasoconstriction by the phenylephrine. Although it isn't exactly desensitization to the drug itself, it is a form of functional antagonism that counteracts the vasoconstriction effects of the alpha-1 agonist. Looking at our model, we can assume that this effect may occur as the 6 to 12 hours falls in line in our phase 2. So if this is the case, then the increased amount of nitric oxide could have allowed for some vasodilation to occur, which could explain why the blood pressure is rising much more slowly in this phase. So now if we're looking specifically at our own experiment in phase 2, we could draw a sigmoidal curve that represents the change from our initial baseline. So that's the initial baseline, and this would be our phase 2. There is a slight increase in heart rate as the baroreceptor reflex resetting causes a parasympathetic withdrawal, which would lead to this increase in heart rate. And the increase in blood pressure, as explained in the previous slide, could have been caused by a multitude of factors, which could have been functional antagonism, as explained using the paper, or due to the resetting of the baroreflex, which could have caused the increase in blood pressure as well.
So now, discussing the third phase of the experiment, we have three main hypothesized responses for why the blood pressure decreases in the third phase of the infusion of the alpha-1 agonists rather than staying the same or continuing to increase. One of these has to do with the fact that the mean arterial pressure raises from 100 millimeters of mercury to 150 millimeters of mercury by the end of the second phase. We can relate this to the previously discussed first SPAD presentation on the paper from Jeffrey Head and Richard McCarty. In this paper, they would increase and decrease the blood pressure in order to generate a sigmoidal curve. To demonstrate the sigmoidal relationship between blood pressure and heart rate. One thing that they took into account during the experiment was that they made sure to avoid blood pressure increases greater than 50 millimeters of mercury from the set point. The reasoning behind this being that an increase this large in blood pressure led to the activation of cardiac rather than arterial baroreceptors, which they had previously shown in rats. Now, what does this mean for our case? This means that we need to consider the possibility of these cardiac baroreceptors being activated. These baroreceptors are within the walls of the right atrium and ventricles of the heart and are involved with the regulation of blood volume. The difference between these cardiac versus arterial baroreceptors is that they are only stimulated by large increases of of blood pressure, approximately 50 millimeters of mercury, in fact, which happens to be the same amount as the increase in our experiment. Just as a bit of an aside, while discussing the structure of the heart, we should also mention some of the structural changes that would be occurring. For the duration of the experiment, there would also be cellular hypertrophy occurring within the cardiac myocytes. This would be caused by the pressure overload triggering a stimulus leading to the enlargement of heart muscles. The physiological effect of the pressure overload would be by increasing the stretching force of the myocardium, as you can see, pushing against the heart, and by increasing the myocardial wall stress, this would then react by causing a greater contractile force in return, which would lead to the increasing development of contractile proteins and assembling new sarcomeres, leading to concentric hypertrophy, contributing to the thickness of the walls. Now, going back to the baroreceptors, if we want to see what happens when we actually trigger these cardiac baroreceptors, we can take a look at the data from the rabbit experiment, which originally showed evidence of their activation, shown here. When treating rabbits with phenylephrine, which is the alpha-1 agonist as previously mentioned, and denervating completely the arterial baroreceptors, there was no large fall in heart rate due to increases in blood pressure up to about 40 millimeters of mercury. But when they increased the pressure beyond that point, a reflex bradycardia occurred due to the cardiac baroreceptors being activated, leading to the generation of the following graph. If we look at the third data set here, we can see a graph that exactly mimics the phases laid out by the experiment that we have been discussing. And you can even see with phenylephrine treatment, the alpha-1 agonist, we can see that the increase, that it begins rapidly, then slowing down, followed by the decrease right here. That is exactly mimicking our experimental data. The problem with this solution would be that the experiment done was due to rapid infusion of alpha-1 agonists rather than a slow increase over a 48-hour time frame, as is the case with the experiment, whereas this was done in just a few seconds.
Although the kidney is primarily a long-term controller of blood pressure, I'm going to quickly touch on the renal involvement in our scenario. So as pressure increases throughout the scenario, so will the juxtamedullary pressure in those nephrons. So the vasorectal capillaries that are not autoregulated will therefore increase the pressure, and that will have the effect of increasing the amount of sodium and water that is excreted and decreasing the amount that is reabsorbed, and that would then lead to a decrease in urine volume with the increase in blood pressure, which causes a decrease in blood volume and therefore a decrease in mean arterial pressure. If we assume that the decrease of 10 millimeters of mercury over the last 24 hours in phase 3 occurred due to a reduced infusion concentration of the alpha-1 agonist, then we will see less of the drug available to act on the receptors, leading to a decreased vasoconstrictive effect and decreased total peripheral resistance, and then a decreased mean arterial pressure. And so the effect that this will have on all the systems that we've talked about will be a decreased total peripheral resistance, decreased arterial pressure, and all of the systems that have been acting to compensate and keep the blood pressure low, like the pressure natriuresis here, in order to decrease the blood volume, that will start to turn off. The baroreceptor reflex will actually go the other way for a little bit. With the decrease in blood volume, there will be a small and minor change in an increase in heart rate as it reaches a new set point. With the change in renal excretion, the blood volume will decrease, and so will the stroke volume, so that will also act to lower the cardiac output over this last phase.